All right, today we're talking about one of the true giants of the 20th century, Niels Bohr. This is a guy who didn't just tweak physics, he completely re-engineered our understanding of reality itself. And then, he had to spend the rest of his life grappling with the world-shattering consequences of what he discovered. So yeah, let's get into it.
Now that sounds like a crazy question, right? But seriously, at the dawn of the 20th century, this was a terrifyingly real problem. All the best science of the day, everything we thought we knew from classical physics, was screaming that everything you see, this screen, your own hands, the entire universe, simply should not exist.
So on one side, you had these beautiful, elegant equations of physics that worked for pretty much everything else. And on the other, you had the undeniable fact that, well, we're here. The world is stable. The two ideas were in a head-on collision. The problem was the model of the atom, Ernest Rutherford's model, which saw electrons orbiting a nucleus like tiny little planets. And that model, it turns out, was a complete dead end.
Okay, so here's the real kicker. According to the known laws of physics, any charged particle that's accelerating, and whipping around a nucleus is definitely accelerating, has to radiate energy. It just has to. But losing energy means its orbit would decay, sending it on this death spiral straight into the nucleus. And this wouldn't take ages, we're talking a fraction of a second. Every single atom in the universe should have self-destructed almost instantly.
Then, in 1913, this young Danish physicist, Niels Bohr, comes along with a solution that was just breathtakingly bold. He basically threw out the old rulebook and said, what if the classical rules just don't apply here? He cooked up two brand new rules. First, he said electrons can only exist in very specific, fixed orbits, kind of like lanes on a highway. He called them stationary states. And while they're in one of those lanes, they just magically don't radiate energy. Rule 2. They only give off or absorb energy when they make an instantaneous quantum jump from one of those lanes to another.
I mean, you can see what a total revolution this was. Where Rutherford saw this smooth, continuous death spiral, Bohr saw these rigid, quantized shells. Where Rutherford's model predicted collapse, Bohr's model created stability, but only by allowing these weird, specific jumps. He didn't just tweak the old model, he slapped a whole new, bizarre quantum reality right on top of it.
And for this incredible insight, for literally saving the atom from collapsing on itself, and for perfectly explaining some other weird atomic mysteries, Bohr was awarded the Nobel Prize in Physics in 1922. He had given us the first picture of the atom that actually worked.
But you know, Bohr's work wasn't the end of the story. Oh no, it was the beginning of a much, much stranger one. Because by saving the atom with these strange quantum rules, he had opened a complete Pandora's box of questions about what reality even is.
So Bohr's answer to all this weirdness was a philosophical principle he called complementarity. The idea is that at this tiny quantum level, things can have properties that seem to totally contradict each other. An electron isn't either a wave or a particle. It's somehow both. And which one you see depends entirely on how you decide to measure it.
Let's just try and unpack that, because it's a mind bender. Imagine you set up an experiment, and your goal is to find evidence of a wave.
Well, guess what? That's exactly what you find. The electron behaves precisely like a wave. It creates interference patterns and does all the wavy things you'd expect it to do.
Okay, but now you change your experiment. You swap out your gear, and this time you're designing it to find a discrete little particle.
And unbelievably, the exact same electron now behaves like a particle. It hits a single, specific spot on your detector. The question you ask of nature literally determines the answer you get. Reality, at its most fundamental level, isn't fixed until you go and look at it.
Now this idea, this fuzzy, probabilistic reality that only snaps into focus when we observe it, that was deeply unsettling to a lot of people, and especially to Bohr's dear friend and his greatest intellectual sparring partner, Albert Einstein.
Einstein famously just couldn't accept it. He believed in a clockwork universe that followed predictable, absolute laws. This idea that at its core, reality was governed by pure chance and probability, to him, that just meant the theory was incomplete. It was an admission of failure.
But Bohr's comeback was, just profound. He basically argued that Einstein was asking the wrong question. Maybe the job of science isn't to figure out what nature is in some ultimate hidden sense. Maybe its job is just to describe what we can say about nature based on our experiments. And if you look at it that way, quantum mechanics was a perfect, complete description of what we can say
But this incredible debate between the titans of physics was about to be completely steamrolled by world events. Bohr's life took another dramatic turn, and the man who had redefined the atom was now forced to confront the darkest possible application of his life's work. He had to go from being a physicist to a global statesman.
So get this, in 1943, Bohr, whose mother was Jewish, got word that the Nazis were about to arrest him. He makes this daring escape to Sweden in a fishing boat and is eventually flown to Britain and then the US, where he's pulled into the Manhattan Project. And there he saw firsthand the terrifying world-ending power that was about to be unleashed.
Bohr saw the future with terrifying clarity. He knew that if this technology was kept secret, it would just breed fear and suspicion and kick off a catastrophic arms race. So his solution, which he called the open world, was basically radical transparency. He argued the only way to survive the nuclear age was for nations to openly share all scientific information, creating a kind of mutual security. He even took this idea all the way to the United States.
And don't for a second think this is all just abstract, dusty theory. The quantum principles that Bohr helped pioneer are the absolute bedrock of our modern world. I'm talking about the transistors in every computer and phone you've ever used, lasers, MRI machines, nuclear power. His fingerprints are on all of it.
And that really brings us to the final, central question of Niels Bohr's life. He started out chasing a fundamental truth about how an atom works. He ended up pleading with world leaders to manage the consequences of that truth. So what's the ultimate responsibility of science? Is it the relentless pursuit of knowledge, no matter where it leads? Or is it the moral duty to handle what that knowledge unleashes? Bohr's life seems to suggest you can't have one without the other.